So again, for the recording, we're still looking at functions. We're looking at whether a function is continuous at a specific number, determine whether what number of a function is discontinuous. So there's three things on here. A has to be in the domain. Okay, there's one of your conditions. That means that it actually has to be part of your function. And you can do that. You can test it by taking a look at, first of all, if the limit is there towards that value, so what you're approaching, and then what it actually is when you get there are all the same thing, right? So, I mean, we looked at stuff, where's my marker again? We've looked at stuff where we have functions that are kind of doing, we have this bit, okay? Would that be continuous? No, there's obviously a gap there somewhere. So that's not continuous. I think in the last lecture, I kept talking about, oh, smooth and continuous, smooth and continuous. It's got to have to flow, but you can't have any missing pieces in there. And that's what they mean by it being continuous. This circle cannot be there, okay? Maybe you even have a certain, where you kind of have something like this, and then the value's up there somewhere. That's not continuous, okay? I mean, the limit exists. But if I plugged in the value for x that belonged there, it wouldn't match up with what the function is supposed to be. It would be something totally different. Okay, does that make sense? That's what our conditions are, okay?
So conditions are for like the actual value?
Yeah, and most of this continuity you can just check. Where's Hank at? Oh. It's usually going to be a visual inspection. You do want to be careful with that visual inspection business because your computers, your calculators, some of them, some of the older models are not smart enough to find that hole. It'll just fill it in because it's supposed to be there, type of thing. I think that some of the newer ones do leave it as a blank in some spots. Definitely your Nspire, if anybody has that, I think that is pretty smart, and it figures out that there is a missing value there, and it'll leave a gap there so that you can see, and then you can try to figure out what that is. Either it's by tracing or taking a look at the table, okay? Alrighty. Okay. So here's our first example. We have this function, excuse me. So we've got this function, and the question is it continuous at 1? Well, do I have any issues with the numerator that I have to worry about here?
No.
What about in the denominator? I could have it. That's if I did have any issues, that's where it'd be at, right? What I can do is I can factor this bad boy. I know that that's going to be x plus 2, x minus 2. If I plug in 1, is that going to do anything to my function? No, right? So I don't really have to worry about it, but I could plug my 1 in here. What do I have? What's 1 minus 1? Oh, that's the wrong mouse. What's 1 minus 1? I mean 1 minus 2, sorry. I said 1 and I looked at it 2. So I've got negative 1, and then I've got 1 squared, which is 1. So it looks like my function is definitely defined as 1/3. So I've met so it does exist with condition 2 as well, because that's what it's going to be approaching, and I think that's it. Yeah.
Okay. So it wouldn't be continuous if it was at 2 then, right?
Yeah, if we use 2 or negative 2, then we would have some asymptotes there that wouldn't be continuous. It will probably go off to positive infinity and then negative infinity type thing. You can take a look at the graph, like I said, if you want to do a visual inspection. But most of the time, those asymptotes are pretty easy to figure out that, yeah, this thing is not continuous. Okay? And it really depends. What am I doing? Oh. What was on top? X minus 1? No, x minus 2.
X minus 2.
X minus 2 was on top.
X squared minus
And on the
4.
bottom I had x to the second minus 4. Minus 4. So if I zoom, let me go zoom 6. You're going to see it shoots down forever, and then it comes back up. Huh. I only have one at negative 2. What did I get?
If you did negative 2, it wouldn't be a whole.
Yeah, because 2 minus 2 is 0, so if you
Well,
have
negative 2
regular
squared is
numbers-
4.
Oh, yeah.
But if I put 4 in there, 4 squared is also. Oh! Someone tell me why it's not, the other one's not there.
Because the top would be 0.
Well, there's no asymptote, but there's a little hole there. And remember what I was saying? It's not smart enough to know, so it wants to just fill in the gap for me. Because it's that, what do we call that? That removable discontinuity?
Yeah.
Okay? So it's not smart enough to know. And I don't know if I see something there. No, I don't see anything. It looks just like it's fine. Okay? So we do have one asymptote, and then we have a little hole that is right there at 2. Okay? But obviously, not continuous. Where am I going? Make myself dizzy. Well, determine whether it's discontinuous. If f is a polynomial function, the limit as f of x approaches, for the function f of x approaches a, has to be equal to the value of f of a for numbers a. That sounds weird, doesn't it?
Yeah.
It's just saying that as you approach, like let's say we're approaching x, and x is 3, and the y value is, I don't know, 5. Make sure that we're approaching 5, and that it's also equal to 5. And if they're not the same thing, then, yeah, it's just like in my example. This is all it's really saying. That what you approach and what it equals need to be the same. Right? Okay. Because if they're not the same, then discontinuous.
It's kind of like.
It kind of is, but that's what I was talking to the other class. Sometimes we just have to write these things out because some people, there can't be no room for interpretation. In last period, we were talking about inverse functions, and there was a rule that said y comma x must be in. So the rule says something like this. For inverses, you guys remember inverses, right? How do you find an inverse? You flip x and y, and that's the rule for that. And people were asking like, why this? Well, it's saying, you know what? You will have x comma y in the inverse as long as this point is actually belongs to f. And they're like, well, why do you have to say that? Well, it's kind of common sense, right? If it's an f, if you want it to be an f inverse, it has to be an f. If it's not there, then it won't be in it. You can't say, oh, because it's an f, it's also going to be in G. We just kind of have to write things out that way sometimes. Have to use all of our English. No, this is not part of this lesson, guys. Oh, you missed the conversation we were having up here. Sometimes we have to say things just the way they are.
Tell it to us.
Math tries not to
The
be.
way it is.
Math don't like to be difficult. Math don't like hard. That's right.
Agree
Okay.
to disagree, everybody.
So let's take a look at some stuff now. Y'all ready? So determine for what numbers x, if any of the following functions, is discontinuous. So we have what's called a piecewise function. Okay, and I want to see if there's any discontinuity in here. Let you guys chat about that for a little bit.
6 and 10.
Just an FYI, yeah, go ahead and turn to your neighbors. You could graph it, but some things that you just really want to look for or really look out for are going to be your conditions, right? Because these are the points where you're switching from one function to the other. Does one really pick off where it left off? Or does it jump somewhere else and now your limits don't exist and therefore discontinues? Does that make sense? Because you could have it in such a way where, hey, you know what? It just happens that my switch from 2x to x squared plus 1 picks right up where the other one's at. But sometimes it doesn't. It jumps to a different y value. So try to figure out if there's discontinuity at any one of these places. And you're going to find that it just might. I think so. It's not bad. I already know.
It was so funny when I was working yesterday because I had my arm was hurting. I was like,
So what's the first thing we should check? Well, what do we want to check? We want to make sure we check 0 and then we check 2. Okay? So let's check 0 first. So if we're looking for the limit at this function as x approaches 0, which one should I use?
The first one.
The first one. And what's 2 times 0? So yeah, that limit does exist, correct? Now I want to take a look at that left hand. Help me out. The left hand limit, and then take a look at the.
Right hand.
Make sure that they are the. That they are apple pie. So let's do this. So as I approach x, the limit as x approaches 0 from the negative side, what value is that? 0, right? What if I approach from the
Positive.
right side, the positive side? So the limit as x approaches 0 from the positive side, what does that equal? Well, if I'm approaching 0 from the right side, I'm not using this one anymore,
We're
correct?
using the middle one.
I'm using the middle one now. So what would I be approaching?
1.
I would be approaching 1. Do the right hand limit and the left hand limit match?
No.
No. So that means that we've got some discontinuity here. There's going to be a jump from 0 to 1. Therefore, yes, there's discontinuity. There's discontinuity when we're approaching 0. Is there discontinuity as we're approaching 2?
Yeah.
Well, we can just
no,
check them, right?
No, there's not. Because a 2 squared is 4 plus 1 is 5. 7 minus 2 is 5.
So this over here is okay. This one picks up right off where the other one left off. But we do have discontinuity when we're approaching 0. Right? Hold up. So I guess the biggest thing here is check those breaks. If you have a piecewise function, see what happens there. If you have rational functions, then check your denominator. That's where the business can happen at, right? Numerator, not so much. Denominator, yes, so much.
Why do you write the M? What is M?
Limit, L-I-M.
Oh, I thought you said.
I write very ugly. It's not L dot M. It's the limit.
The arrow is.
Well, now it all makes sense. What? What's wrong with my arrow?
It looked like a 70. Oh.
Oh, yeah.
It does look like a 70.
Limit negative x negative 7. X minus 7.
I got it. Got it.
You know what? It's already the end of the year, and
Don't say well, it's a recording. Keep your eyes open when you say this. Oh, that's scary. His eyes will pop out.
Yeah, it's already the end of the year.
Just like that. No. What's happening?
Limit of. Are you doing calligraphy? That's weird. I don't like it.
What's wrong?
what are you doing to me, man?
Why is it square? It's a square.
I give up. Guys, that's everything.
That's it?